Hi, everybody. My name is Julia, and I come from the Department of Electrical and Computer Engineering in Aarhus University. And I'm about to present to you the research done on biodegradable temperature sensor, which is a result of my master thesis. So it was a very time-constrained research, but I think successful. In the outline, I will explain my motivations and goals for the research, as well as explaining the materials and methods used and the results and discussion. So, of course, the motivation here is the sustainability. The ever-present e-waste issue is addressed in my research. What my use case is medical equipment, healthcare equipment that needs to be safely discarded after use. Mostly, we talk here about the difficulties of cleaning and sterilizing the medical equipment. So we want to use it as a single use and then safely throw it away without any environmental harm. So the goals for this research was to develop, fabricate fully functional printed temperature sensor with high flexibility to conform medical use, as well as high biodegradability that comes from water solubility. So let's start with the substrate. For the substrate, we use polyvinyl alcohol substrate, which is a polymer substrate, biodegradable and highly water soluble. It is highly bendable, as you can see on the picture, and smooth with minimal impurities, which is good for the printing. We made a 3% PVA solution, which was later poured into a ceramic dish and mixed and poured into a ceramic mix and then dried in the temperature of 50 degrees Celsius, left there overnight in the oven. For the temperature sensor, I used a Mandarin shape RTD, and with the dimensions you see on the screen, I used a drop-of-demand piezoelectric inkjet print with the drop spacing of 45 micrometers to achieve the best resolution I could get in the lab. The cartridge voltage for this specific the specific inks that I used was 25 watts. In the end, I ended up fabricating two temperature sensors. So the one on the left you can see is the P.PSS sensor. So the conductive and sensing material is P.PSS. And on the right, I also developed the same sensor, but using a silver conductive material, just as a way to benchmark and compare the performances of these two. So the temperature sensing was done by placing the sensors, the fabricated sensors on a heat plate and measuring the resistivity they output at the 10 degrees Celsius increments. And on the left, you can see the values for the silver sample, which are, as expected, pretty good with a really nice linearity and really low resistance. And on the right, we have our P.PSS on PVA sensor. Because it's a polymer, the conductivity with increasing temperature goes down. Oh, the conductivity goes up, the resistivity goes down. The P.PSS displays a little less linearity in our measurements, but still the drop in resistance between the low temperature value and the high temperature value is pretty significant, which means that it can be used to detect a high spikes of temperature. Additionally, we made the temperature sensor reliability test by cycling the temperatures. So the resistor was measured at 100 degrees and 30 degrees to see how well the resistance will come back. What are the differences in the measurements at the same environments and the same parameters? And our cycling test came out really good with very reliable measurements. Lastly, we tested the biodegradability of the temperature sensor in water. So I put a fresh PVA sheet, a silver print on the PVA substrate, and the PSS print on the PVA substrate in water, and tested it with measurements or results documented at 2 hours, 24 hours, 48 hours, and 7 days. And so as you can see on the pictures, at the 7-day marks, the substrate was basically completely gone and dissolved. You can see that the clean one has the best results compared to the ones that were printed. It is suspected that the PVA display a little less water solubility properties after being exposed to high temperatures, such as, for example, a very high temperature measurements. So after 130 degrees, I could see the decrease of solubility in the substrate. It was also tested in soil with over 6 days. As you can see, the results are also very satisfying after 6 days of leaving the device in the soil. The base was almost completely gone. Both of the materials are biodegradable and biocompatible, so there is no waste left in the soil. So in the conclusion, the biodegradable printed sensor was fabricated using PVA substrate and a P.PSS conductive material via the drop-on-demand piezoelectric inkjet printing method. The fabricated sensor is very flexible, water-soluble, and biocompatible. And the biodegradable sensor shows good linearity in the temperature measurements taken in the range of between 30 and 110 degrees Celsius.